have left several things sort of undone. And in today's class, I want to take things up systematically and just finish off several proofs. We will also make a connection back with non-linear spaces. So without further ado, let's get started.
Hello, sir.
Yes.
Sir, in the previous class, when we were discussing about continuity at all points for a function, then you mentioned one characterization as f inverse of any ball intersecting the range contains a ball. This implies continuity at all points, but I mean, I do not understand how that is sufficient for being continuous at all points.
So this is a proof that we are going to do today. So let's get started. Okay, so yeah, and also I should start recording.
Recording in progress.
Very well. So this is what we are going to do today. So as usual, work in a metric space X. And remember that this means that we have open balls. We have open sets, which are arbitrary unions of open balls. Open sets are unions of open sets are open, finite intersections of open sets are open, and so on, right? Closed sets are complements of open sets, etc. So we will systematically see this. So closure of some subset S of X. So continuity of a function f from a metric space X to metric space Y in terms of topology. And today's exercise, which I will just state verbally if you want to sort of have something to think of on your own, is that we are going to state various equivalent characterizations. You can see which of these statements continue to make sense and continue to be valid for arbitrary topological spaces as opposed to metric spaces, right? Topological spaces are a wider class, so you can take this as an exercise. All right, so and let's suppose I have a point small x. We say that this is a limit point of S if the following thing happens. So what happens? Every neighborhood of X contains a point in S which is different from X. And then we saw an equivalent characterization. And what was that? There exists a sequence Sn with what property?
None of the points are equal to X.
Yes, but where is this sequence? The sequence is in S, remember? And what property should this sequence satisfy? Come on, this is obvious. Converges to X, exactly. So remember, this definition does not take a stance as to whether X itself should be in S or not. It may or may not be. Okay. So we saw the equivalence of these two. Essentially because what? So recall the idea. So what was the idea? That if I take Sn, if I take us, okay, so here is the thing, remark. So recall, and this is sort of what the proof turned on. If I take Sn in a ball of small radius around X, and if these radii go to 0, then what can I say about this sequence? Then automatically, what happens? Come on, this is all should
We
be
have a sequence that converges to X.
right. And in fact, this particular sequence will converge to X. Right? You're taking first point within distance 1, second point within distance half, third point which is within distance 1/3, and so on and so forth. Perforce, this sequence is going to fall into X. Okay. Then automatically Sn converges to X. And I think maybe we had these curly braces in notation. Anyway. And of course, instead of 1 over n, I can really have any sequence of numbers that is converging to any sequence of positive numbers that converges to 0. All right. So let's have all the chain of things from yesterday and prove the equivalence. So recall that what was S bar? This was, by definition, the intersection of all closed sets containing S. So I'm going to write this notation. So this is the intersection of all T such that T is closed and T contains S. So a couple of things to remark about this. So we call this the closure of S, and we are going to prove a number of properties, equivalent definitions, which we stated last time, and I left you as exercise. So I'll go through it quickly today. But one thing to point out is that so this is the smallest closed set containing S. The smallest closed set, of X containing S. All right, and let's see very quickly why this is the case. This really is essentially for language reasons, along with, so one by one. Why? Why does this contain S? Because each T contains S, right? So their intersection is going to contain S. Why is this closed? Because
arbitrary intersection of closed
exactly
sets.
Because it's an intersection of closed sets. Because it is an intersection so but this is the interest. This is the, why is this the smallest closed set? And really, there is no mystery about this. The reason why it is smallest is because
If T, if another closed set T dash is a superset of S, then T is also a superset of S bar.
why is that? And okay, let me just write down. Because any, see, smallest such that what? So I have to take smallest over a family. What's an arbitrary element of that family? A closed set containing S. So any closed because any closed set containing S. That's what the description is, right? The smallest closed set containing S. So among all the closed sets containing S, I have to show this is the smallest, but it's actually, in a strong way, it is the smallest, because any such is one of the T's. You see, I'm taking intersection over all these T's. And therefore, the intersection of all of the T's is going to be contained in all of the T's. So that's all that is being said. And hence contains S bar. Okay. So this is really true for linguistic reasons. The only math part was here. Over here was just the fact that an arbitrary intersection of closed sets is closed. Now, this is a general theme in math that happens in several situations. That if I take intersections of certain kinds of sets or structures, then it also happens to be one of those. So have you seen some examples of this before?
I think we saw something similar with vector spaces.
Right. So if I have subspaces of a vector space, then intersection of arbitrary subspaces is a subspace. And this semester, you probably have already seen what a group is. So and subgroups. So intersection of arbitrary subgroups of a group is a subgroup. It's a group in particular, and it's a subgroup, and so on, right? So intersection of subrings is a subring. Intersection of ideals is an ideal. Intersection of normal subgroups is a normal subgroup. So this is a standard construction that is often done. So there's some minor remarks. So I took the smallest closed set containing S. What about the smallest closed set contained in S? Is there such a thing?
Phi is closed, so I guess it would just be that.
No. So S is an arbitrary subset of your metric space X. Is there such a thing as the smallest closed set of X contained in S? I'm just playing with language here.
Empty set.
Yeah, so this is dumb, you see, because the empty set is closed. So that doesn't really give anything interesting. And likewise, I can play, instead of smallest, I can play, say, is there a largest closed set containing S? Yeah, again, it's dumb, the whole space, right? So other variations of this don't really give anything interesting. But here is a question. Can we have something similar to this for open?
So if we could, this definition would not necessarily make sense anymore, since an arbitrary intersection need not be open.
Right. So, okay, right. And similarly, one of the four possibilities I did not say, which was that the largest closed set contained in S. Because if you took all closed subsets and took their union, closed subsets of S and took their union, it need not be closed. So you see, just because I can utter a phrase doesn't mean that it makes sense, right? So of the three just sort of unthinking variations of this phrase that are possible, two of them are dumb, and the third one doesn't really make sense. You can similarly consider for open sets something analogous to this, and there is one useful definition which I will just write down. Anyone? So remark. Can similarly consider largest open set How should it go?
Contained in S.
Contained in S.
Exactly. Contained in S. And largest works well, no? Because I just take whatever is inside and I just take their union. It still stays inside. So this deserves a name. This is called interior of S. Okay. And you will see all of these things in topology. So I don't want to go too much in this direction. But there was one idea earlier somebody suggested after class to try to use something called the boundary. So you can maybe now consider what should be called the boundary of an arbitrary set using both of these things, the closure and the interior. Anyway, so this is an aside, but let's go on with our main theme. Yes.
Sir, I had a question about this definition of closure. So like the closure itself is closed, so it will be in the intersection. So does that cause problems like when defining it? Or
no, but that is after the fact. No? You see, the definition makes complete sense. I'm taking the intersection of. You see, the fact that this is a closed set is a result of the definition, and the fact that arbitrary intersection of closed sets is closed. There is no circularity here.
Right. Yeah, I got where I was confused. Yeah. Thank you, sir.
Okay, so we had other characterizations of closure. So let's write this down as so equivalent definitions. And I just want to write down. So S bar is equal to intersection of T closed, T contains S. And I rewrote this because last time we remember we gave names to these things. So we call this A, let's say. So it's a bit informal. I'm temporarily calling the set defined by this equality to be A. And then we had others last time, right? So this was what? So this is equal to S union the set of limit points of S. Then we had, so we called this B, then what was C? Those X such that there is a sequence in S converging to for some sequence in S. Here, I'm not insisting that this sequence be distinct from the set S itself. And finally, X such that every neighborhood of X intersects S. And okay, so I'm running a bit out of space over here. So this was definition C. Sorry about this. B. So last time we sort of, I waved my hands around here a little bit. So let's be a bit systematic here. Sorry, not definition. So proof of equivalence. All right. So I want to show that I am going to still leave part of this to you because this is exactly the kind of proof that when you sit down and think through, there is nothing to it, but you have to go through it. Right? So A is ND because A complement contains a D complement. And why is that? Let us see this. So what is A complement? Because, so this is the first part. What is A complement? Let's just write this down. Notice the, so when I take the complement inside the ambient space X, intersection turns into union. So union of what? union of. So it's going to be the union of the complements of T's. Now complement of T is going to be open. So let's call this. So union of all open sets, I'm saying V. So T is supposed to contain S. So what is that saying about the complement?
The complement
Does not contain
is
S.
contained in S.
No, be careful. So I want T to contain S. That means the complement of T has what property?
It does not intersect with this.
It does not intersect S. So you see S is some set here. T contains S. And so this is the T complement that cannot intersect S. That's what the with V intersection S is empty, right? And what is the complement of D? Oops, okay. All right, I think we can do this. What is the complement of D? So I have to take the negation of the condition. So if you want to be in D, that means that every neighborhood should intersect S. What is the negation of that?
There exists a neighborhood which does not intersect S.
Right. And if the neighborhood does not intersect S, then I can take the open set inside that neighborhood if necessary, which will not intersect S. So this is equivalent to saying there exists open neighborhood of X, which is disjoint from S, such that V intersection S is. So of course I gave the game away because I'm going to call this also V. So do you see this?
Sir, neighborhood is itself an open set always, right?
No, for us, we want to have the flexibility that a neighborhood X of a point is a set that contains an open set containing X.
Okay, sir.
Right. But over here, if you just think about it for a moment, this is neither here nor there. So in particular, open sets containing X are also neighborhoods of X. So clearly, each X in correct, because every X has this neighborhood V, and A complement is the union of all such V's. So it will in particular take X also. Right. So again, there is now here is the exercise part of it. I'm going to show only one-way inclusions, and part of your exercise is your exercise to show all the reverse inclusions. This is not difficult here at all. It really is going to just take the same words and write them backwards appropriately. But I want you to go through the exercise in your mind to get comfortable with the words. So you are going to do all the reverse inclusions. All right. So the next one is I'm going to show that D is contained in B. So let us see this. All right, so every neighborhood intersects S. So take X in D. I want to show that it is in B. So again, just follow at this level, just follow your nose. So that means I have to show that it is either in S or a limit point of S or both. So I may say, suppose X does not belong to S. And now it is enough to show that X is a limit point.
So we have proved it, right?
Yes, exactly. But again, you see, there is very little to prove over here. So one nice thing is that I have two ways of thinking of limit point. One in terms of sequences and one in terms of every neighborhood containing a point in intersecting S in a different point. But you see, I mean, it just writes itself. There is nothing to this. So X is not in S. What does it mean that this point is in D? It means that every neighborhood of X intersects S. What do I need to show that it's a limit point? That every neighborhood of X intersects S in a point other than X. But that's automatic because I assumed that the point X was not in S. So the intersection of any neighborhood, so by D, any neighborhood of X intersects S. In some point, in a point that has to be different from X because X is not in S. X is a limit point. So you see the nature of these proofs. There is very little action happening over here. A lot of it is just rewriting. All right, so again, the reverse inclusion that B is a subset of D is something I'm leaving for you. I will most likely ask you to do several of these things in the homework. So it is better that you do it on your own, okay, before the homework is due. All right, so now let us show that B is a subset of C. Okay, so what is C saying? I have to show that points in S as well as limit points of S satisfy condition C. That means I have to produce a sequence. So what's the idea?
So if it is in S, then we have the constant sequence of the elements itself. Okay. And other than that, by definition of limit point, we can have a sequence.
If X is a limit point, take a sequence guaranteed by definition of limit point. So you see, I'm playing it both ways. This idea, this characterization of limit points that I had in terms of open neighborhoods as well as limit point, as well as sequences is coming in handy. All right. So this is an exercise here. And in fact, let me make this even sort of clearer. Not show as in your minds. Write proof of all reverse inclusions. Okay. So let's even put a box around this. I really do not know to what extent you can write, and I'm saying this individually to each one of you, okay? I do not know to what extent you can write a correct and a clean mathematical argument. Those two are separate words, by the way. Your argument may be correct and being correct without being clean, so that it is god awful for other person to read. I'm sorry to use that word, but you really need to, it's a separate skill to write something that is easily readable by somebody else. And, I'm just going to sort of insist that if you're not there, then this is a course where I insist that you make substantial progress. Okay. So one is that you should be able to write cleanly and you should be able to write correctly. Okay.
Excuse me, sir.
Yes.
Second, please explain me the D belongs to D is a subset of B, that question.
Okay, so D is all right. So let us let's see if we can. All right. So what is D saying? That every neighborhood of X intersects S, right? And I want to show what is B, that, okay, so did I make a mistake? No, okay, so fine. I want to show that a subset, I want to show that a set is contained in a union of two sets. So I may do this. So if I want to show that some set, P is contained in the union of Q and R, then I have to take a point in P and show that it belongs to Q or it belongs to R. So I may do this by saying that take a point in P. If it does not belong to Q, then it has to belong to R. That's going to be my layout of the proof. So notice, so that's why I started by saying, okay. So I'm taking something in D. It is enough for me to say that if it does not belong to S, then it has to be a limit point. That's the set theory part that I just did, right? Okay, so I know that this X satisfies the definition in part D, and I may assume that it does not belong to S. Well, what does D give me? It says that every neighborhood of X intersects S. But because I have validly assumed that X itself is not in S, the intersection of this neighborhood, any such neighborhood with S, has to be a point other than X. That was the definition of a limit point, X being a limit point. One of the two definitions. Right, so I hope this helps, but if it does not, yeah.
Yes, I get it now.
All right, so let's move on. Yeah, so write a proof of all the reverse inclusions. I'm sort of demanding that each one of you sits down and really does this. The target audience is who should be able to follow whatever you have written. Okay, so let's see where we are. Yeah, just give me a moment, please. Right, good. So we can now move on to continuity. So I have so now take X and Y metric spaces. And I have a function f from X to Y. So first let's write down. So what is the point now? We are going to see several ways of formulating what it means for this function to be continuous. And there is some genius in this, in these reformulations. It is not difficult to prove. The interesting thing is to formulate it, to realize that such a formulation is worthwhile. And we will see some payoffs of this. Okay, but first our definition, the epsilon delta definition. So is continuous if it is continuous at each point, right? So that means at every point, something must happen. So let's write down, that means for all A in X, it is continuous at. So what does it mean? For all A in X, if I'm given any epsilon greater than 0, then there exists delta greater than 0, such that, all right, so such that what? As soon as I take a point X, that is at a distance less than delta, what should that imply? Distance between f of X and f of A is less than epsilon. Of course, notice one thing over here, the order of quantifiers is important. So in particular, you can say that delta depends on what does it depend?
Epsilon and A.
Epsilon and A, right? If it does not depend on A, then what do we say?
A uniform continuity.
Uniform current continuity, exactly. So, all right. But this is the definition. This is just the straight definition that you saw last semester. The only difference is last semester, instead of d of x comma a, we just said absolute value of x minus a. Okay. All right. And this semester also we are going to use it mostly in that context only. It is just that instead of absolute value, we are going to think of it as a norm. Very well. So let's just reformulate it, which is to say that for all a in X, F inverse of any ball around what? So we have done this now twice. Once I think may have been after class, but last time we did this carefully. So what was the upshot? F inverse of any ball around
F of A.
F of A. What about this inverse image? What should be true?
It should be contained in a ball around A.
It should contain a ball around it.
So just be careful. I'm just going to write this down. A ball around A. So this is bad. A ball around A, but okay. So which way is the containment? Be careful. See, I want to show that everything in this ball around A, that is everything. By the way, what is the radius of the ball around FA from the sentence above?
Any radius.
Any radius, but what in the statement above, what was the radius?
So epsilon.
Right?
Epsilon.
Correct. And what we want to say is that everything within radius delta from A should land within the target ball, right? So the containment, be very careful here, is that this contains a ball around A. Okay. Now, so this is what.
Sir,
Yes.
sir, is this essentially a proper subset?
No, but a subset. All right. So if it's proper, then one writes something like this, no?
Yes, sir.
So I'm not taking any position, right? We do not want to take any position.
Okay, sir. Okay.
It just contains, that's all. So if you like in your notes, right, instead of that symbol, you just say contains a ball around there. Maybe, you know what? I'll just say contains. But now let's go a little further. So this is the same thing as saying that 2 F inverse of any open set, of course, in Y. Now, F inverse of ball around F of A. So that ball means in Y, using whatever the metric that Y has, is open in X. So a clean formulation. And let's prove this. Proof of the equivalence, that is. The proof of the equivalence. So what's the easy direction? 2 implies 1 or 1 implies 2? Anyway, it's not really much, but and last time we did this, so this time I want to be a bit more efficient. So 2 implies 1. Again, you just look at the shape of what is to be proved and just write down obvious sentences. Use definitions. So how should the proof begin? F inverse of any open set in Y is open in X. I'm given this, remember? And I want to show the first sentence, but I will not use epsilon and delta. I want to show that F inverse of any ball around F of A contains a ball around A. That's what I want to show. So how do I start? How do I use the fact that F inverse of any open set in Y is open in X?
Open balls are open sets in Y.
Exactly.
So we can start with that.
So take open set in Y to be ball around. So, okay, so let's see. Not I should really have started. You see, so 2 is given and I want to prove 1. That means the thing that is given to me as a task in my hand is I am given any ball around F of A, right? And I want to show that F inverse of this ball contains whatever. So a ball is given to me. So take open set in Y to be the given ball around F of A. So what do we know by hypothesis? By hypothesis, that is by 2, F inverse of this ball is open. And a very dumb but needed observation, and contains notice the given ball is around F of A. So F inverse of that certainly contains the point A, no? But look now, I have an open set is open. So let's call this, let's call this something, let's call this W. So I have this W and I have this A. But I have a point inside an open set. So what do we know? Therefore, W contains a ball around A. And of course, that's the ball that I'm going to take to be, sorry, not B epsilon A. This should be, sorry, 1 second. I'm just getting lost in my notation here. Yeah, so sorry, this is not epsilon. This should be, that's the one. I mean, if I want to relate it to my epsilon delta definition, then this is the delta that I should take. But you see, I'm done over here. Inverse image of this open set contains a ball around A. So I'm done. So was this a completely empty proof? No. There was this little fact that if I am given an open set and any point in that open set, then I can put a ball around that point in the open set with the given point as at the center of the ball. This was a very easy consequence of triangle inequality, but nonetheless, it's a basic fact. A ball, so I will read, so with centered at A. Okay, so this is 2 implies 1. Let's do 1 implies 2. All right, so what is the shape of this now? What should I, so what is given to me? I'm given this whole epsilon delta business. And I want to show that F inverse of any open set is open. So how do I show that a given set is open?
Union of open balls.
I take any element in it.
Correct. Let's make names, right? So take take A inside F inverse of open V in Y. Right. So I've just set up some terminology. And I need to, and I need to show that I have to, that I can put a ball around A inside this inverse image. So let's do it. Follow the nose. So which is to say, i.e., it's exactly the same thing as f of A is in open V in Y. Those two statements are synonymous. So what do I get to do? Look, now f of A is in an open set. Put a ball around it. So sum B epsilon f of A is in V. Now what? Therefore,
So this epsilon is not according to our desire, right? I mean, we cannot put anything to be the radius.
we are okay. So this is the point f of A, and this is the set. All right. In fact, let me take the set to be something like this. This is V. All I'm saying is I can put a ball around this f of A. I'm not saying that this ball will have arbitrary radius. If the radius is too big, then it will go outside. But the local nature of openness says that I can put a ball with center at f of A that is entirely within V. So I'm choosing a particular epsilon.
Okay, sir.
Right. But you see, what does my definition tell me? Definition tells me that if I give you an epsilon, then you will be able to give me a delta. So that's the delta that I'm going to take. So by 1, what do I get? Some B delta of A is in F inverse of V. Now this delta, if you really want, delta depends on A. So if I want this dependence, then I can write this delta sub A. But I don't really want to do that and make the notation complicated. So what have we shown? Notice, to sum up, we have shown so notice what we did. For every point A that was in F inverse of V.
Hello, sir.
Yes.
Sir, the B delta of A, I mean, we choose it such that it is contained. Oh, okay. Sorry, sir.
That is, but here is the key thing. This is, we have used the fact that I'm given that the function is continuous, right? Okay, so now just see something dumb here. F inverse of V is just the union of the singletons A over F inverse of V, right? But in fact, what have we done? We have said that for every A, I have put a B delta a ball with centered at that point, all of which is in F inverse of V. So you see the right hand side, what I have written does contain F inverse of V just by what it is ranging over. But continuity gave me that I can put a small ball around each A, which is in F inverse of V. So F inverse of V is open. End of the story. Okay, so so let's move on. Again, so these proofs, if they're not coming easy to you, then what that tells you is that you're just not yet comfortable enough with the terminology. It's okay. So sort of my guarantee is that it is perfectly okay if this is not easy, but the guarantee is that if you spend some time, it will become easy, where you will reach a stage where even if you do not see the proof, you will just see how to write it down and the proof will write itself out. Okay. So that is number 2, but we also have other characterizations. So further characterizations. So F is continuous if and only if.
So I think it's confusing that you have written some B epsilon FA belongs to V, because like we are using the fact that for all epsilon we'll get a delta, and here we have for one epsilon we are getting a delta, so that is true. But I think it would be better if we write B epsilon 1 or something, so that would mean that this is fixed. I mean, otherwise.
Okay, but you see, this is the thing. This is correct as it is because I'm
Yes,
saying
yes,
some.
yes. Okay.
Not every, correct?
Okay.
I mean, if you want, so the thing is, in general, I dislike subscripts and
Okay. Yeah.
subscripts and dash and double dash. But that's just me. If it helps you, if you're thinking of epsilon as a variable in your mind, and if you want to take a particular value of that, you're welcome to take a different letter. So
sure.
All right. So F inverse of any closed set in Y is closed in X. And what is this? This is a one sentence thing. So I'm just going to say, because what happens? F inverse of Y minus any set S is equal to, well, how do complements behave under inverse image? Inverse image of complement of S is complement of inverse image of S. So X minus F inverse of S. There is nothing to this. And in fact, I'm going to give this as a set theory exercise for you. Exercise. For F X to Y, any set map. F inverse preserves all unions, intersections, complements. F inverse works very well with this.
Does F need to be injective?
Check. All right. If you have a doubt, check. And then this brings in the next question. What about F? And the answer is it really does not work nearly as nicely. So any conditions on F under which the situation is nicer. So this is just set theory. If you have not seen this before, then at some point in your life, you have to get this out of the way and just sort of keep it with you. Simple set theory, nothing else. Okay. So this is an aside really. So let me put this in a box. Now, okay, let's continue. F is continuous, continuous continuous.
Sir,
Yes.
sir, what do you mean by situation is nicer?
Okay. What it means is the following. See, this is how mathematics is kind of done. In that, so I'm not asking you to prove something or disprove something. I'm just saying figure something out, like find out a nice statement. So what's going to happen is that if the previous statements, maybe some of those will be true, but some at least will be false. That F will not preserve unions or intersections or something, right? So my question is, can we have a statement where maybe it does preserve, but only for some kinds of Fs? Can you put some interesting condition on F under which a desired statement is true? This is not a difficult thing, but you will see. See, in mathematics, often when you're trying to do new mathematics, nobody is telling you what to prove. You first have to figure out what to prove. And sometimes, not always by any means, but sometimes figuring out what to prove is the hard part. Maybe proving it is easier. So the short answer is that it is deliberately vague, because I'm asking you to find the statement to prove. But it's not hard. Anyway, so here's another one. F of S bar equal to F of, sorry, I don't want to make the mistake that I made yesterday deliberately. For any subset, and this is a straight exercise. Because you will really do this in point set topology. So if you want to do it, do it. If not, you can leave it. And also number 5. And this is important. So last semester, you proved a criterion for continuity, right? In terms of sequences. What was it? Suppose I have a sequence xn converging to A in X. What if the function f is continuous, then what has to happen?
F of xn has to converge to f of k.
This sequence has to converge to. I'm sorry, I'm being a bit sloppy. I think in our sequence, in our notation for convergence, maybe it was written in curly braces, but sometimes I will forget this. And this is an if and only if condition. Okay, so now my question is, do we want to prove this? Okay, so I'm going to say proof. Proof of 5 is exercise. But again, you have to write this down. But here, this time, let me just try to get you at least started. So let's spend like 2 minutes on this. Which is the easier direction? So let's write down our definition, which is 1. So 1 implies 5 or 5 implies 1. Which one is easier?
1 implies 5.
1 implies 5. So let's just sort of get started. If I want to show 1 implies 5, then just by the way the statements are set up, what are the statements that I should just write down in the beginning, just for free?
F is continuous.
F is continuous. So I have all of these things. I have all this epsilon delta business, or I can think of it in terms of balls or open sets if I want. Which one would be better here? The epsilon delta definition, or just in terms of balls without using any epsilon delta?
Epsilon delta.
Yeah, because you see, what is it that we have to prove? we have to prove convergence of something or the other, right? And convergence of some sequence. Convergence of sequence is defined in terms of epsilons, right? Okay. So one thing, I'm given the epsilon delta definition. What else am I given?
Xn converges to A.
So I'm already given this sequence. That means that given any epsilon, I'm able to find some n such that beyond that point, all the xn's lie within distance epsilon from A. That is already given to me. Okay. And I want to do the same thing for the sequence f of xn, right? So you see, the ability to choose any epsilon and finding corresponding capital N is given to me for the sequence xn. I want to do the same thing for the sequence f of x. So what is the challenge that is given to me? Now I'm given an epsilon. How do I find the delta? Oh, sorry, that was the wrong thing. How do I find capital N? How do I find this capital N? I want the f of xn sequence eventually to be caught within this small epsilon that is given to me around f of a. So what do I do? So let's start the proof. Given sorry, not and. What do I do? For example, should I take this epsilon and find something for the sequence xn?
Hello, sir.
Yes.
Sir, in the definition 1, I mean, if we consider the epsilon to be, I mean, if we consider the epsilon to be equal to delta, then we have that d of fx comma fa is less than is. Sorry, sir. I need to formalize a bit more.
All right. So let me just point out something. You see, it makes no point to use, it makes no sense to use that epsilon. See, the epsilon that is given to me needs to work in for the sequence in y. It makes no sense to use that epsilon inside x. I first have to connect x and y, and the only means of doing that is the function f. But I do know something about the function f. It is continuous. So first find delta such that what happens? X, oh, sorry, x minus a. I'm sort of giving the game away. The way, so what am I doing? Whatever we did for real numbers by taking absolute value of x minus a, I'm just going to replace those things by the distance between x and a and just run the exact same argument. Okay. So such that, in fact, you know what, let's write this in terms of balls just because we have find delta such that f of delta ball around A lands inside epsilon ball around f of A. And now what will I find? For this delta, I will find a capital N such that beyond that point, all the xn's lie within distance delta from A. But if all the xn's are now within distance delta from A, then what do I know about f's of everything?
So fxn is within fa, I mean epsilon neighborhood of fa by the definition of continuity.
Right, which is what I wanted. So you see, etc. I'm going to say etc. And now, in exactly the same way, this proof also, I'm going to say you do. Adapt. Better still, since you did this last semester, don't look at that proof. Because you have learned a style of thinking last semester, right? So bring that style of thinking to bear on this. And there is something interesting over here. You will see what strategy of proof is good. Again, follow your nose. See what's required. Okay. If you get stuck, there is a general recipe. If you get stuck in doing some problem, spend some time, half an hour, 1 hour. Don't spend 5 or 10 minutes. Minimum half an hour. After that, go to some source. Read the first sentence of the proof. Does that first sentence now begin some kind of thought process? If it does not, then read the second sentence. The moment you find something unexpected or something that you felt, oh, okay, even if this is true, I don't see why they're saying it here. Stop at that moment and repeat the process. Okay. So, anyway, so with this, I am going to now draw a line under this. Okay. So why all this song and dance about these definitions of continuity? Various ways of thinking about continuity. Let's see one by one. Okay, so one comment here. Remember the exercise that I asked you to do right at the beginning? I didn't write it down. Which is whatever development we are doing, what part of this development is valid for, makes sense for an arbitrary topological space and then is valid. Okay, so for closures, I allow you to think of this on your own. Let's see for continuity. Does number 1 make sense for any topological space?
No, we don't need to have a notion of distance.
We don't, right? The only thing that is there in a topological space is open sets. But look at number 2. It's beautiful. That statement makes sense for any topological space if X and Y are arbitrary topological spaces. So what do? I turn this property now into a definition. I say a function f from a topological space X to a topological space Y is called continuous if it meets this, if it satisfies this. This is a very common thing in mathematics, right? For example, when you make definitions, and you did this in myriad times in school. So let me not rant for very long. But you see, when you define sine, cosine, and tangent, for example, you first defined it for right angle triangles. But then it didn't really make sense if your angle was more than 90 degrees. But then you said, oh, okay, I will see it within the using the unit circle in the plane, and I will adapt these definitions. You did this for defining what it means to take a real number raised to another real number. You first raise something only to integer powers. What does it mean to raise to 0 power? What does it mean to raise to minus power? You use some properties of the earlier definition as a guideline to extend the definition. A similar thing is at work over here. All right. So with second one as a definition, then you can make sense. Does number 3 make sense? Yes, and it is equivalent. Does number 4 make sense? Do we have closure of a set in an arbitrary topological space? The answer is yes. It's the smallest open set. It's the smallest closed sets, right? But the question is the equivalence also going to hold in an arbitrary topological space? So anyway, if you want, you can think about this. But anyway, there is no hurry. So if you do not want, if you do not feel the itch to do this, there is no need to do it, because anyway you will be doing this at a later point. Okay. So we are almost out of time, but I do want to do something at least a bit. So properties, examples. Continuous functions. So here is one thing, sort of value of a good definition. So everything is a metric space. or even topological space for that matter, doesn't really matter. FG continuous implies so is their composition. But of course, it is not F composed with G, it is G composed with F. Is obvious. With number one, maybe you have to do a little bit of work. But number two makes this completely obvious, you see. Inverse image of open set is open. So you just take inverse image of open, it stays open. Inverse image of that also stays open. So inverse image of the composite is open. Right? So obvious. Okay. Completely dumb point, which I will not even write down. The identity map is continuous. But here is another thing. Is this obvious? Inverse image of open set is open, but inverse images inverse images preserve intersection. So it is enough to show that inverse image of a ball is open. What is the inverse image of a ball in X, in S?
I think it's the ball intersection with S.
Yeah, but ball intersection with S is really the ball in S, you see, because the metric is inherited. No? So the topology,
Yes,
right? So you see, inverse image of ball is by definition the ball in S. So of course, this is continuous function. Then maybe let me end with exercises. So just indulge me for a couple of minutes, please. All right. So let's start going towards norms, because finally we want to do real numbers, right? And Rn. So Rn to R. Projection onto, so let's call this pi sub I. Projection onto any coordinate is continuous. So the rest of this is exercise, okay? And again, you can do this. This is not difficult. But what I want you to think of is that how is the topology on Rn defined? Well, it's defined via metric, but the metric comes from norm. Now, which norm do we use? We have lots of norms. The one that we visually want to use is the usual Euclidean one, right? Take square roots, take square all the coordinates, add them, take square root. But we have said that in some ways, what norm you use does not make a difference. And we are going to make that precise. I wanted to do that today, but we will do it right at the beginning of the next class. So the thing that I want you to ask yourself is a simple point, but under which norm is this easiest to do? Okay. Then, okay, so these are all exercises. Suppose I have a function from X to Rn. And so this is simply goes to f1x, fnx, right? So this is f, so that f is continuous if and only if Okay, I think maybe this is enough. I mean, there are several others, but I don't want to overload you. Also, we are out of time. So please try to do these exercises. We can discuss a little more after we stop the class. And the last thing I want to say is that read about equivalence of knots. Okay, so with this, let's stop the class for today.
Recording stopped.
Sure, from where?
This is so standard. Oh, sorry. So this is so standard that you can read it from anywhere. The definition. I mean, if you want, if you in fact might as well. I'll write this down. And again, let me say this. Okay, so feel free to leave anytime. So everything that we do after class will be discussed once again in class. It is just that if you want something more to think about, or if you have any questions, then I'm happy to answer. So are there any questions, by the way, before I do anything more?
Well, I had a question about the continuity for topological spaces, our definition.
Okay.
So on metric spaces, there are like the name continuous makes sense to me, because we're sort of saying if we move a very small amount, where a small amount is given by our distance function, then like we've moved a small amount like in the range also. But this does not make sense for a topological space. So do we call it continuity just because it's a generalization from continuity on metric spaces, or is there some other way I can visualize that?
So I don't know a good answer to this question. Okay. But I mean, what would satisfy you? For me, this is a satisfactory thing that this is a definition that it's a conceptually simple definition that turns out to be equivalent to something that we intuitively understand. Okay, maybe I can try to say a little more, but look around, people, you may find better answers. Is that, see, inverse image of every open set is open. So if you think of open sets as being something small, then and open sets as having wiggle room, then what this is saying is that no matter how small I make my target, no matter how small I keep my error margin, allowed error margin in the target, then that is something that is guaranteed by limiting a certain error margin, right? So, I mean, if you see, there are sort of two things about open sets, that open sets are small, at least, they're not always small. There are topologies where open sets are not small. But open sets are small, but more importantly, open sets are local. That is, at every point in an open set, I have a wiggle room. So this idea that an inverse image of an open set is open means that if I take any point in the inverse image, then I should be able to go in all directions. But let me not say anything more because I could just be babbling. I think let's put it this way. The definition, a virtue of a definition is that how useful is it? And this one has proved tremendously useful. Even in topological spaces where your intuition of what is close, etc., may not make sense. Even over there, this definition has proved extremely useful. So.
Okay, I think that makes sense, sir, and that is satisfactory, sir. I was just wondering, like, why we called it continuity in particular, but I think this wiggle room, like intuition.
I mean, see, for example, why do we say that 2 to the 0 is 1, or how does it make sense that 2 to the minus 1 is half? Does it make sense? Does it make sense? Well, we are really saying that, look, I have these very nice laws of exponents and I want them to be valid. So I will just extend my definition so that it works. I don't know. I mean,
Yes, sir.
So I don't have a better answer. If you find a better answer, you let me know.
All right, sir. Yeah. Thank you, sir.
Yeah. So let me ask you a question. Last semester, when you defined sort of continuity, at that point you must have. Did you define that addition is continuous, for example?
I think we did.
Okay, but continuous in what way? What does it mean that addition is continuous? As a map from where to where?
Oh no, sir. I think we didn't talk about like we said. I think what we did is that like if I add two continuous functions, their addition is also continuous. That's
Right,
what we did.
right. But you see, addition as a map is from where to where?
From R2 to R, or actually just the Cartesian product of X with itself to X in general.
Right. I mean, well, for a general vector, I mean, by the way, this will not make sense for a metric space. It doesn't mean anything to add points. But if I'm in a vector space, or let's just stick with real numbers, then addition is a map from R2 to R. So you can add, right, X comma Y goes to X plus Y. Now it makes perfect sense to ask, is this map continuous? And of course it is going to be. I mean, if this map is not continuous, then maybe we should just throw away our definition of continuity. So yeah, this map is continuous. So now these are exercises for you to try to prove that addition is continuous. Multiplication is continuous. Division is continuous, suitably away from zero.
Sir, I was wondering something, like if you had, let's say, a continuous map that's also bijection between a topological space without a metric and a metric space, does that sort of allow you to associate a metric with the one with the space that hasn't been endowed with the metric to begin with?
Okay. So let me just repeat the question. The idea is the basic idea, as I understand, is standard and simple, in the sense that if I just have a bijection between two sets, then I can use, and if one of those sets has a structure, then I can just use that bijection to transfer the same structure to the other set, right?
Right. Yeah, I was just wondering if that happens.
But what you said is more subtle than that, in the sense that here you're not taking just a metric space and another set that is in bijection. If that is the case, then what you're doing is just renaming. But you see, your question is asking for more. You're saying that, oh, but look, I have a metric space X and I have a topological space Y. So topological space Y already has its own connection of open and closed open sets, right?
Yes, sir. Yeah.
Right. So, so you see, if there is an arbitrary function between the two, then there need not be any kind of connection between the two. I mean, see, for example, I can take the usual topology on R, and I can take the bijection of R with itself, which is given by identity. But I can give the topology to R, which is the most ridiculous topology that you can think of. Well, there are two ridiculous topologies, but one of them is just declare all sets to be open, all subsets. There is absolutely no connection with like what is close to what. It's a topology. I mean, it's all subsets. So everything is. So you see, the identity map here is not continuous. This topology is not induced by any metric. Oh, well, no. Let's be careful over here. This topology is going to be, sorry, just a moment over here. Yeah, this topology is induced by metric, and you can think about which metric this is. But okay, maybe let's take a completely different topology. The other ridiculous topology on any set, which is that any non-empty set, is that the only open sets are the empty set and the whole set. That's a topology.
Okay, but yeah, in this one,
But this is ridiculous, right?
But it wouldn't be a bijective map between the two then.
No,
Wait,
it's
no, sorry, it would be,
no,
yeah, but it won't preserve.
Right. So the bijective map is not between the collections of open sets. The bijective map is between the underlying sets themselves.
But it wouldn't be a continuous map though, right? Because
okay, exactly. So this is the thing, right? So this is the thing, and I suggest that this is a very good question. Even with the examples that I have given you, you should be able to see that the answer to your question is no. For a fairly, it is an excellent guess. But there is a very basic obstruction over here that you will be able to see even using these dumb examples that I gave. One of the dumb examples. Identity map between real numbers with usual topology and some dumb topology.
But I think the one with
you see,
no
one way the map is continuous. From which one to which one is it continuous?
So is the order significant? Because I was asking, like, it could be continuous, either way, right? I mean, between the space with the metric and the one without the metric, or even from the one without the metric to the one with the metric. It doesn't seem like it would be significant, but is that really the case?
Right. Okay, so think about the question, but just sidestepping the question, if you want this to work, can you think of a stronger hypothesis that will do the job for you? So you said there should be a bijective map from X to Y that is continuous, or a bijective map from Y to X that is continuous. One of them metric, one of them only topological space.
Right. Yeah, that was
right.
Yeah.
But can you make this stronger in such a way that all right. So I want to motivate this. This is an basic but very interesting point. What is an isomorphism of vector spaces? How do you think of it?
As something that preserves the structure, like, let's say, of addition and multiplication in the vector space.
But I want to say it's isomorphism. So if something preserves addition and scalar multiplication, then it's
right, which is also a bijection. Like it has to satisfy both those.
Yeah. So this is right. You see, this is a valid definition, but you should really put this definition out of your mind, sort of forever. It's a consequence. A more natural definition. Okay, so let's even go to sets. What is a bijection from one set to another? A map F from a set S to a set T is called a bijection if
it's injective and it's also surjective.
Yeah, or that's not a good definition.
Or maybe if you think in terms of left and right inverses.
But so a map, So a map F from X to set S to set T is called an isomorphism of sets if there exists. Continue.
Wait, to fill in the definition for.
So if there exists a map G from T to S such that.
Well, such that okay. Wait, this is just generally for any two sets, not any particular objects, like let's say vector spaces or anything like a
Yeah, I
general
mean
definition of
any two
isomorphism.
sets, but then I want to take this to other kinds of things. See, okay. So the point is,
I'm not
you
exactly
have,
sure how to define an isomorphism between just any two arbitrary sets without
well, I
knowing what
mean,
the
so let me just
structure
do it, because I'm making a bigger deal of it than required. But what I'm trying to say is that a map F from a set XS to set T is an isomorphism if there is a map G in the reverse direction, such that, can you complete now? Very simple. Such that the composition both ways
is the identity map.
is the identity.
Right. Okay.
Now, this is what you want to take elsewhere. So even for vector spaces, what is your definition going to be? A linear map is called an okay, and before that, so a map is called an isomorphism if this happens, and when are two objects isomorphic, if there is an isomorphism between them. So when are two vector spaces isomorphic? If there is a linear map from V to W, F, and a linear map from W to V, G, such that the composition both ways is identity. Now it so happens that for both for sets as well as for vector spaces, if I have a bijective linear map or a bijective map, it is automatically an isomorphism. What you will see is that for topological spaces, it is not true. It is not true that a continuous bijective map is an isomorphism.
So in what way do we have to actually strengthen the condition to get an isomorphism?
You have to separately say that there should be a continuous map F from X to Y and a continuous map G from Y to X, such that the composition both ways is identity. See, the point is that
the form of the definition stays the same even for.
Right, but the point is, if you want to state it your way, then the hypothesis should be not just that there is a bijective continuous map. There is a bijective bicontinuous map. That is, both the map as well as its inverse should be continuous.
Okay, I see. So it is significant to include both the.
But you see, for example, if you take real numbers with the ordinary topology, and from this you take the map to real numbers where there are only two open sets, empty set and the holes. Is this map continuous?
Yes, sir, because pre-image of R is R, which is open, and pre-image of Phi is Phi, which is open.
Yeah. And in fact, if you think about it, this is true for any map between any sets. Inverse image of empty set is empty. And inverse image of the whole space is the whole space. So this map is continuous, but it makes no, and it's bijective, but it makes no sense to call these topological spaces isomorphic, right?
Right. And in the other direction,
map the other way around, it's not continuous. There are so many open sets whose inverse image is not open. Okay. So this thinking sort of goes in the direction a little bit of category theory. Try to think in terms of everything in terms of maps. The maps are more important than the objects, and try to express everything in terms of maps without using elements or words like injective, surjective. Expressing things in terms of maps makes it more intrinsic. It's early to start. Maybe just keep it at the back of your mind. What I'm saying, because right now, me insisting on this is purely what is the word? Sorry, I'm missing the word here.
So even
it's unjustified ideology at this point. It's like exactly. So you can just think of this as a potentially interesting way to think that you might want to check out at some point.
Thank you, sir.
Okay. Another couple of exercises that I just want to mention, which is, so let me write this down and then let's stop.
So this thing you said that this isomorphism between vector spaces is a much more special case than like that will not satisfy the condition of isomorphism for metric spaces. Even I so this is a while back even I was thinking about this. So I mean I felt that this is kind of weird that there is a theorem that says that a linear map is bijective if and only if it is injective. So that's why I at the beginning when we were taught linear algebra I couldn't find like the perfect connection between functions and maps. So now there is like
No, just one second. You're saying several things. First of all, a linear map is injective if and only if it is surjective. That is not true.
no bijective. I mean
Yes, but even that even that is not true. You're missing a very important. You're missing an important caveat over there. Between what kind of vector spaces?
I guess real or complex. I mean it's written in Professor Ramdas's notes. So.
Yeah, but right, and he's absolutely right. But the point is between only finite dimensional vector spaces.
Yes. My bad. Yeah.
Right.
Yeah.
See, but you see that you should think of this finite. It's exactly like finite sets. A map between two finite sets has a 2 out of 3 thing, right? Suppose there is a map between two finite sets, then any 2 of the following 3 properties implies the third. The map is injective, the map is surjective, and what's the third condition? The cardinality of the two sets is the same. Yes?
Okay, yeah.
But this is not true for infinite sets.
Okay, I see.
Right? Consider the map from Z to Z, which is multiplication by 2. The two sets have the same cardinality. This map is injective, but it's not surjective.
Yes. Okay.
Right? However, for finite sets, this is true. And the theorem that what you just mentioned about vector spaces is exactly the analogous thing. You should think of this as heuristically exactly the same. And notice what happens though, but you cannot take a set map. A linear map between two vector spaces, if it satisfies, any two of the following properties implies the third. The map is injective, the map is surjective, and the two vector spaces have the same. What takes the place of cardinality?
Dimension.
Exactly. So whichever way you did this using rank nullity or pivots or whatever, it's the exact parallel statement.
Yes.
Okay, but I don't know what you were getting at. But here, what is true? I mean, what we said today really is not related to what happens for vector spaces, because the phenomenon that happened over here does not happen for vector spaces. Over there, if I have a linear map that is bijective, then it's automatically an isomorphism, because just the inverse map, the set theoretic inverse map, is automatically linear.
Okay.
Right? This is what is failing here. If I have a bijective map between two topological spaces, which is continuous, its inverse will exist as a set map because it's a bijection, but the inverse may not be continuous.
Okay.
Because continuity is something that sees not just points, but the collection of open sets.
Yes, I follow.
Okay. But in any case, in this course, I really don't want to go too much in the direction of point set topology. Just introduce some language, that's all. Okay. So let me just write a couple of exercises here, which if you want, you can do. So what is notes here? Right. So R cross R to R, the maps plus times as a consequence, you can say that Rn to R, x1 to xn goes to some p of x1 up to xn. P is equal to polynomial in n variables. As an exercise. And I think with this, I don't want to say anything more. So this is just exercises continued. Okay, so if there is nothing else, then let's stop for today and then we will continue on Friday. Does anybody have anything? Very good. So let's stop and we will meet on Friday. Bye.
Thank you, sir.
Thank you, sir. Bye, sir.